The year 1766 marked a pivotal moment in the history of chemistry, a moment illuminated by the meticulous observations and groundbreaking experiments of Joseph Priestley. His work, meticulously documented in experiments and observations on different kinds of air, represents a cornerstone of pneumatic chemistry, laying the foundation for our modern understanding of gases and their transformative roles in chemical reactions. To appreciate the originality and profound implications of Priestley's endeavour, we must first understand the intellectual landscape that preceded his investigations. Prior to 1766, the concept of air was largely understood as a homogeneous, indivisible substance, while some alchemists, notably Jean-Baptiste van Helmont, had recognized the existence of distinct airs or spirits. The gas sylvester released during the fermentation of wine. These notions remained largely isolated, lacking a systematic framework for investigation. The prevailing phlogiston theory, proposed by Georg Stahl, dominated chemical thought. Phlogiston, a hypothetical substance believed to be released during combustion, became the central organizing principle for explaining oxidation and reduction. This theory, while providing a semblance of order, also imposed conceptual limitations. The true nature of air, and its varied interactions with other substances, remained largely a mystery. Priestley, therefore, entered a scientific world primed for a paradigm shift, a shift that, in large part, Priestley's approach, as revealed in experiments and observations on different kinds of air, was fundamentally empirical. He was a keen observer, a meticulous experimentalist, and a man driven by an insatiable curiosity. His experiments were characterized by their ingenuity and the careful attention he paid to detail. One of his most significant innovations was his use of a pneumatic trough, a device that allowed him to collect and manipulate gases over water. This seemingly simple apparatus proved to be an indispensable tool, enabling Priestley to isolate and study various airs, including what he initially termed nitrous air, now known as nitric oxide. The method involved reacting metals with nitric acid, a reaction that produced a gas he then collected. Priestley observed that nitrous air readily combined with air, forming a red-brown gas. This observation was a critical step towards understanding the complex chemical reactions that occur between different gaseous substances. The narrative of Priestley's experiments unfolds with a logical progression, meticulously cataloguing his observations. The first significant discovery within the volume is isolation of what is known as oxygen. Priestley obtained this gas by heating red mercury oxide, a substance he obtained by heating mercury in contact with air. Priestley noted that a candle burned more brightly in this newly discovered air than in the standard atmosphere. He also observed that mice lived longer in this air, and he, himself, breathed it. He described this dephlogisticated air, as he called it, as being remarkably pure and supportive of both combustion and respiration, a crucial divergence from the established phlogiston theory. The identification of this previously unknown gas was a monumental achievement, one that would forever alter the course of chemistry. Beyond his discovery of oxygen, Priestley meticulously investigated other gaseous substances. He experimented with fixed air, that is, carbon dioxide, discovered by van Helmont. Priestley demonstrated that fixed air could extinguish a flame, a property he utilized to carbonate water, creating one of the earlier forms of carbonated beverages. He also studied inflammable air, what we know as hydrogen, and its explosive reaction with air. His investigations extended to the study of different gases produced by various chemical reactions, thereby expanding the understanding of the composition of air beyond the established parameters. Each experiment was carefully documented, generating an unparalleled wealth of. The immediate impact of Priestley's work was profound. It stimulated intense scientific debate and spurred other researchers to replicate and extend his experiments. His detailed methodology provided a blueprint for investigating other gases. His discoveries challenged the prevailing phlogiston theory, which struggled to adequately explain the properties of dephlogisticated air and its role in combustion. The implications of his research extended beyond the laboratory. It had the potential to revolutionize industries such as medicine and food preservation. Priestley's work served as the catalyst for a new understanding of matter, with the first serious challenge of the phlogiston theory ultimately sparking revolutionary discoveries. The influence of Priestley's work can be clearly traced in the contributions of Antoine Lavoisier, a name synonymous with the chemical revolution. Lavoisier, building upon Priestley's observations, conducted his own experiments, which led him to name and properly characterize oxygen as the element essential for combustion. Lavoisier's quantitative experiments, where he carefully measured the weights of reactants and products, provided strong evidence against the phlogiston theory. He demonstrated that combustion was a process of combining a substance with oxygen, and that oxygen was consumed, not simply absorbed, from the air. Lavoisier's work, though built upon Priestley's initial observations, transformed chemistry into a quantitative science, setting the stage for the atomic theory and modern chemical understanding. The influence of Priestley's work also extended to the broader scientific community. His experiments sparked a flurry of activity. Several scientists began to investigate the properties of gases. Henry Cavendish, in England, isolated and characterized hydrogen, calling it inflammable air. Carl Wilhelm Scheele, a Swedish apothecary, independently discovered oxygen, albeit slightly before Priestley, though Priestley was first to publish his findings. The discovery of other gases, such as nitrogen and ammonia, followed quickly, each building upon the foundation laid by Priestley's pioneering work. The systematic study of gases became a central focus of the burgeoning field of chemistry. Priestley's work, however, was not without its critiques. The most significant of these stemmed from his unwavering adherence to the phlogiston theory. He interpreted his observations in terms of phlogiston, struggling, for a significant period, to reconcile his findings with the emerging oxygen-based chemical theory. This adherence, while limiting his complete understanding of the reactions, did not diminish the importance of his experiments or the profound impact of his discoveries. The conceptual framework shaped his interpretation, yet he had still unlocked a rich new field. The very act of attempting to fit his observations within the structure of phlogiston theory forced him to conduct and publish even more research. His steadfast conviction in the prevailing theory did, ironically, contribute towards its eventual the reception of experiments and observations on different kinds of air was complex and multifaceted. The work was initially lauded for its novelty and the ingenuity of its experiments. The Royal Society, of which Priestley was a member, recognized the groundbreaking nature of his work. The book was widely read and discussed, yet, as the evidence against the phlogiston theory mounted, the initial enthusiasm for Priestley's interpretations waned. While many acknowledged his experimental prowess, they began to question his theoretical framework. As evidence mounted to support Lavoisier, the genesis of Priestley's work derived from several sources. Firstly, he was deeply influenced by the work of Stephen Hales, whose book Vegetable Statics explored the study of air in plant respiration. Hales' work had paved the way for pneumatic chemistry. Additionally, Priestley, as a dissenting minister, was driven by a sense of intellectual curiosity and a desire to explore the natural world. His experimental approach was also informed by the scientific method of his era, which valued empirical observation and meticulous documentation. His personal connections, including his friendship with Benjamin Franklin, further fueled his interest in scientific pursuits. Franklin's influence instilled in Priestley a sense of curiosity. The direct influences on Priestley's work are several, and include the aforementioned contributions of Stephen Hales. Priestley was also strongly influenced by the work of Robert Boyle, particularly Boyle's Spring of the Air, which advanced understanding of air's physical properties. John Mayer's Tractatus Dua had also introduced the notion of a spiritus nitroaereus involved in combustion, a concept that indirectly influenced Priestley. These individuals and their work provided the initial intellectual framework, with Mayer's work proposing a nitroaereus concept. However, Priestley's genius lay in his capacity to build upon these prior conceptions, translating them into groundbreaking experimental results. The enduring legacy of experiments and observations on different kinds of air lies in its transformative impact on the field of chemistry. Priestley's meticulous observations and groundbreaking experiments laid the groundwork for our modern understanding of gases and their crucial role in chemical reactions. His discovery of oxygen revolutionized scientific thought, challenging the prevailing phlogiston theory and paving the way for the chemical revolution led by Lavoisier. The impact is still felt today with the range of fields, including medicine's study of atoms. Priestley's work also served as a catalyst for the development of new laboratory techniques. His use of the pneumatic trough, for example, became a standard method for collecting and manipulating gases. His detailed experimental methodologies served as a model for other researchers. He demonstrated the importance of careful observation, precise measurement, and rigorous documentation in scientific inquiry. His work helped to solidify the transition from alchemy to modern chemistry. In conclusion, experiments and observations on different kinds of air by Joseph Priestley stands as a landmark in the history of science. His relentless curiosity, his ingenious experimental designs, and his meticulous observations revolutionized the field of chemistry. He, inadvertently, overturned the prevailing theoretical framework, and his discoveries transformed our understanding of the composition of air, the nature of combustion, and the very essence of chemical reactions. While his interpretations were rooted in the prevailing phlogiston theory, he paved the way for its eventual overthrow, laying a foundation for modern chemistry. His work serves as a testament to the power of observation, experimentation, and the relentless pursuit of knowledge, leaving an undeniable imprint on the scientific landscape.